Okay, we want to use Euler's identity to help us find real valued solutions. Let me really quickly remind you of the situation that we've got. We've been working with this differential equation. We want to solve it. We found its characteristic equation, and we found that its roots, the solutions, are a pair of complex conjugate um, numbers plus or minus square root of 7i. Um, so that leads to two solutions. And you see these two solutions here. The problem, though, with these solutions is that these solutions are complex valued. And, as much as I've been extolling the virtues of complex numbers, our real interest is in, pun not intended, our real interest is in finding real valued solutions. Okay? That is to say, um, solutions which only take values in the real numbers. See, like if I plug in, for example, fancy real numbers. I mean, typically, if I plug in a real number into this expression here, I'll get some non-real complex number out, and I don't want that. Okay, what I really want is something which is real valued, so that I can interpret it and use it and that sort of thing, right? Because that's sort of the game that we've been playing generally. So how do we do that? Well, we invoke this trick, which I'm sort of shoving down your throat and asking you to believe. Maybe I can try to explain it. If you're given some kind of complex valued solution, and I should say non-real complex valued solution, then the real and imaginary parts of that complex valued solutions are themselves real valued solutions to the differential equation. So in other words, the real and imaginary parts of y1 here are themselves going to be solutions to this differential equation here. Now, I hope that that's somewhat plausible, because when you if you think about y in terms of its real and imaginary parts, like let's say it's u plus iv, what's the second derivative of u plus iv? It's the second derivative of u plus I times the second derivative of v. So when you plunge all of that data into your linear differential equation, well, it's like the real parts and the imaginary parts are just going to always stick together in some way. And they'll never kind of interact. And so, because the result that you get out is this number 0, and since 0 is equal to 0 plus 0i, you can set the real parts equal to each other, you can set the imaginary parts equal to each other, and what you're going to find is that those real solutions, the real part and the imaginary part, are real valued solutions. Okay? Um, how, though, do we find the real and imaginary parts? So this is where we're going to use Euler's formula. So let me just quickly remind you about Euler's. I keep calling it a formula, but it's really an identity. It's stronger than just any old formula. It's an identity. Very powerful stuff. And it says the following. E to the I theta, where theta is a real number, is, and this is actually true for all theta, but we only care about the real number case. Cosine theta. Sorry, when I say all theta, what I mean is even if theta here happens to be a complex number. Cosine theta plus I sine theta. This is what it says. And much like other identities, this is one that you should have tattooed or engraved on your bones, so that when you are exhumed by the alien race that will visit planet Earth after we are long dead and gone, they will find this again on your femur bone. Okay. In other words, memorize this. This is what I'm trying to tell you. Memorize this. Okay, very useful. How can we bring that to bear to breaking down this guy right here? Y1 equals x square root of 7ix. How can we use Euler's identity to break that down into its real and imaginary parts? I'm going to show you. So y1 is equal to, and maybe I'll write it in more in alignment with what we got here. It's e to the square root of 7ix. Okay, now I know how I've written it here, okay? And I have a certain logic in my head for the order in which I write things. But will you agree with me? If I take theta, oh my goodness, if I take theta here to be square root of 7 times x, this is my theta. That's a real number, okay? And what I can do is replace the theta in Euler's identity by square root of 7 times x. Put square root of 7 times x here, and therefore there, and therefore there. Okay? And what this allows me to do is rewrite e to the square root of 7 ix as, and I'll get rid of this purple stuff, rewrite it as cosine of square root of 7 times x plus I sine square root of 7 times x. Okay? Now, we see immediately, don't we, what the real part of y1 is and what the imaginary part of y1 is. Here is the real part of y1. Maybe I'll write it like that. And here is the imaginary part of y1. Maybe I'll write it like that. And what I claim, and I'm right, is that these are solutions, real valued solutions to the differential equation. Okay? Let's check it real quick, okay? Let's check that y1, maybe I'll just call it y equals this cosine square root of 7 times, my goodness, square root of 7 times x is a solution. And I'll let you check the other one because it's very similar. So then what's y prime? Well, that's square root of 7 with a negative sign, negative square root of 7 sine square root of 7x. And what's y double prime? Well, it's negative square root of 7 times square root of 7, which is 7, times cosine square root of 7x. Okay? Now plunge all of this in. Maybe I'll copy my differential equation here. There it is. Duplicate. 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 Down here. Put all of this, I don't know why I did that. That was a total waste of time. Plug all of this information into here, and what we get out is negative 7 cosine square root of 7 times x. That's y double prime, plus 7 times y. What is y again? Oh yeah, it's written right here. It's cosine square root of 7 times x. And what is that? Oh my god, it's 0, right? This is equal to 0, which is what we want it to be in order to satisfy our differential equation. So in other words, check mark, a green check mark, okay? In other words, this really is a solution. And I'll let you check that sine of square root of 7 times x is also a solution. And in fact, this real part here and this imaginary part here are linearly independent solutions. So given that that's the case, we can then write down the general solution. So let me write down that as a comment. So you can check that y equals sine square root of 7x is also a solution. And that these two solutions are linearly independent. So maybe I'll write that. Can I just write Li, please? Are linearly independent. Okay? So what does this mean? What in the end? This means that the general solution to my differential equation is a superposition of these two solutions. It's y equals c1 times cosine of square root of 7 times x plus c2 times sine of square root of 7 times x. Okay? Every solution to this differential equation can be written in this form for some C1 and C2. Okay? All right. Now, this was a particularly simple example. Why? Because our roots turned out to be purely imaginary numbers, square root of 7i and negative square root of 7 times I. What happens if our roots have a real part, which is not 0? So let's tackle that in the last video, where we'll solve one more example, and we'll make it a initial value problem this time. Okay, so see you in the next one.